Okay, ladies and gentlemen, let's go ahead and start. I hope you can hear me. Nick, can you hear my voice?
Yes,
Okay, perfect, great. And I think you should be able to see the slide.
I can see
So,
them.
okay, wonderful. So, good morning to those of you to whom it's a morning, good afternoon, and good evening to those of you for whom it is evening. It's evening here in Arizona. It's about 5:30 p.m. So there was a question during the last session that was about a DIVR. The last session 2 days ago was about voltage regulators, and one of the kinds of regulators is a DIVR. Student had a question about that, so I just created the slide to talk about it. A DIVR, okay, let me maximize this, is basically a dynamic integrated voltage regulator. We had talked about the fiber and the MBVR, the motherboard voltage regulator, and then the fully integrated voltage regulator that's on the chip. So DIVR is a kind of regulator that's actually on the chip. So this is a little more advanced possibly than just the plain fiber. And what it does is it dynamically adjusts the supply voltage to different parts of the chip based on the performance needs. So if there are different parts of the chip, so one part is asking for more power compared to another part, then this would actually adjust the voltage going to that part of the chip depending on the performance requirement. So depending on performance needs, power consumption, and the thermal conditions. So the chip would kind of monitor to see if any parts are overheating and will prevent too much power going to an area that's overheating, and that can limit the performance of that part of the chip. So this is the type of regulator that operates within the device itself rather than relying on external voltage regulation components. And it's also very highly optimized for fine-grained power management. So that dealt with that question. Are there any other questions from the last session? Okay, if there aren't any other questions, you're welcome to put questions into the chat as well. And once we're done with some of the lectures, or the mini lectures, I'll go ahead and handle questions. So today's topic, I am going to share the first lecture slides, share screen there. Then I am going to maximize the screen. Okay, so we are starting today's session dealing with transmission line theory, and then we move on to signal integrity. So the concept of a transmission line, the idea behind a transmission line is to transmit a signal, for instance, from one place to another. So on the left-hand side here, is the text. On the right-hand side is a kind of a bit of a schematic that kind of shows you. So here's a voltage source, which can send power and or a signal. And here's the impedance associated with the source. We talked about the fact that impedance is kind of like the resistance, but applied for alternating current circuits and for signal circuits where the currents and the voltages are changing. And then we can see, okay, I need to minimize my Zoom window so I can see the slide. Yep. And then over here, this is symbolic of the transmission line. And that is the transmission line that's the inductance or resistance in this case. And the text here is basically making the point that the wavelength for the signals that are propagating in the transmission line is c, which is the speed of light divided by the frequency of the wave that's propagating. So a transmission line is basically an electrical structure that's designed to conduct electromagnetic waves in a contained manner. It can be anything from a wire to a bus to a hollow fiber and so on, and we'll see some examples. The length of the electrical structure in this case is comparable with the wavelength of the waves that are propagating through the structure. And the time that it takes for the wave to travel through this structure is not negligible. So it's not instantaneous. So there's a little bit of a delay, and that's something that we have to build into and take consideration of in the circuit. So here are some examples of different kinds of transmission lines. So planar transmission lines, these are typically used in packages and in printed circuit boards. We also have non-planar transmission lines that are used in cables, radio frequency communication, and optical usage. So if you look at the planar transmission at the top left-hand side, you can see that there is a metal line that has a certain width W, a certain thickness T, and it's placed inside a dielectric material. So it's like an insulating material around this, and it has an H height, H above it, H below it, and yes, so the metal line is completely encapsulated. It's inside the dielectric, and this configuration is called a strip line. In contrast to this, the second structure is one where you got a metal line here with a certain width and a certain height T that's sitting on top of a dielectric. And that dielectric has a height H. That's called a microstrip as opposed to a strip line. If you look at the third structure to the right, we can see that we have a coplanar waveguide. So here what happens is you are actually transmitting a wave inside the guide here with certain width, and there's a certain spacing S between the waveguides sitting on a dielectric medium, which could be SiO2 or a silicon oxide, silicon nitride, or different kinds of oxides or nitrides, and that is a certain height. All of these measurements that are provided here will come in later when we are talking about what the effect that these have on the transmission. In the case of non-planar transmission lines, here is a coax cable that has a central metal wire surrounded by, it can be, so if you, yeah, it can be dielectric and then a metal layer. Yes, so commonly it would be like some kind of a dielectric and then a metal layer. The dielectric can be a glass, for instance, and the key parameters here are the radius, the inner radius, and the outer radius here. Here's an example of a hollow metal guide where you've got a hollow metal conduit and you have the waves that are propagating inside this conduit. Here's an example of an optical fiber where you have a glass fiber where the glass composition is optimized for the wavelength of light that you want to propagate. And around that, you have cladding material. And the cladding material is chosen such that the light of that particular frequency will totally internally reflect at the interface between the glass core and the cladding material. Then outside this cladding material, you can have more protective sheathing material. So typically the dielectric constant, epsilon1, of the core is greater than epsilon2 of the cladding material in this case. So moving on, we have seen this kind of a structure before where you see we model a component or a board or the bulk silicon with a resistance, an inductance, and a conductance and a capacitance. The resistance and the inductance are in series, the conductance and the capacitance are in parallel. And so a transmission line, which is a long line that we are sending a signal through, is modeled as a series of these units, the same units repeated as many times as is needed to match the length of the line. So the elementary components here is the distributed resistance. The circuit representation is a series resistor over here. The units are ohms per unit length. And what it does is it contributes to conductor loss, basically heating because of resistance that loses some of this. It decreases the amplitude of the signal and it heats up and loses some of the energy due to heating. L over here, that's the inductance. Again, distributed inductance, and it's modeled as a series inductor. Its units are henries per unit of length. And what it does is it is correlated with the magnetic field around the wire. So if you've got a wire and if your current that's flowing through the wire, it creates magnetic field lines circularly around the wire. And there's energy that's stored in those magnetic fields. C is the capacitance here. And it's modeled as a shunt capacitor. So it's a parallel unit rather than a series unit. And the units are farads per unit length. And here what happens is this stores charge on the conductors. So these two, this conductor, and there's a dielectric, an insulator between the two of these, this behaves as if it's a capacitor. So it's storing charge and electrical energy as a result of that. G is the distributed conductance, which is it's modeled as a shunt resistor. Sorry about that. So it's modeled as a shunt resistor, and its units are Siemens per unit length. Okay, let me put that off. Okay, my apologies. So G is the distributed conductance, and that's modeled as a shunt resistor as opposed to a series resistor. Its units are units of conductance, which are Siemens per unit length. And what it does is it's contributing to dielectric loss. That is, there's a certain amount of leakage of charges through the dielectric. That's what it's modeling. So what we're doing is we're considering the transmission line as an infinite series of two-port elementary components with an input and an output, each representing a infinitesimally, that's a very, very small, short segment of the transmission line. So when we're actually modeling this, you then integrate this behavior across the length of the line. Moving on, one of the key constitutive equation or sets of equations that are used in software models to model the behavior of the signals in these lines is it uses what are called the telegraph equation or the telegraph equations. And here's a representation of them. We'll see a little more explanation of this in future slides. So just as a reminder, we have students from a wide variety of backgrounds, ranging from undergrad students to professors at different universities. And both the students and the professors come from different backgrounds themselves. Some are in electrical engineering, some are in chemical engineering, some are in materials engineering, and there may be other forms of engineering and science represented as well. So I have to teach at a level that everybody can understand. So to some of you who are in electrical engineering, this may be just a repeat of what you already know. The telegraph equation is a fundamental concept in transmission line theory, which describes the behavior of the voltage and the current along the transmission line as a function of both time as well as distance. So the equation basically is dealing with the physical characteristics of the line, like resistance, inductance, capacitance, and conductance, as we saw on the previous slide. And it helps to model how the electrical signals propagate down the line. So as the signal moves, so if you think of a peak that's traveling down the line, there are different things that can happen to the peak. One thing that can happen is attenuation, which means that the amplitude drops, phase shift, which means that the signal does not stay synchronized in terms of its phase, it can get shifted, and distortion, the shape of the signal can change as well. So we'll go over some of this as we look at these in the following slides. So the key characteristics associated with these, the telegraph equation and the behavior of the signals as they are transmitted down the lines. The first thing is the resistance per unit length, which corresponds to energy losses as heat because of the atoms in the line basically provide they resist the motion of the electrons, for instance, and that heats up the line and there is some loss of energy. Inductance, what it does is it represents the magnetic field that's created when you got a current traveling in a line. There's a magnetic field that's created around it, and there's energy that's stored in that field. The capacitance is it's again per unit length, and it represents the conductor's ability to store electrical charge between two conductors. So if you've got two conductors like this, and you've got a voltage difference between the two of these, and you've got a dielectric in between, that behaves like a capacitor, and that stores electrical energy. The conductance per unit length, this represents the leakage current through so you got a metal, another metal, and then leakage through the dielectric. That's what it represents. And so each of these have details that we will talk about here. So we're on the next slide now, the physical interpretation of the telegraph equations. Wave propagation. The equations describe how the voltage and current signals propagate down the transmission line in the form of waves. the solutions, so you'll see, and we'll talk about this. So these are basically differential equations, as you know, right? So this is basically it's a single differential, dv over dx, and here you got a second differentiation, right? So d squared v over dx squared, and then we got some kind of a relationship there. When you try to solve these equations, the result is wave functions like sine waves, cosine waves, or exponential waves. So the solutions to these equations are typically wave-like functions, which are sine or exponential. And what this means is the signal will travel along the line and will experience delays that are based on the distance and the properties of the line. So that's the wave propagation. In addition to this, you have attenuation, which means a lowering of the amplitude, and distortion. The shape of the wave will change due to the resistance and the conductance terms. So there's a loss of signal strength, and there's also phase distortion. So higher resistance or higher leakage results in greater energy dissipation and greater energy signal degradation as a function of distance. Continuing to the next slide. So now we're talking about what these things mean physically, right? In addition to this, there's dispersion and reflection. The inductance and the capacitance, they affect how the signal's phase velocity changes with frequency. So the speed of the wave as it propagates down the line is different depending on the frequency of the signal, and that's called dispersion. So the combination of the L, the inductance and the capacitance, can cause different frequency components of the signal to travel at different speeds. And so a high frequency signal may reach at one time and a lower frequency signal may reach at a different time. And that can result in distortions as well. In addition to that, there is a reflection. If there is a mismatch in impedance at the end of the line or at different points along the line, you can end up with signal reflecting backwards. And so there's a signal loss due to that. So key concepts in these equations are signal propagation, how the signals move, impedance, which is the ratio of the voltage to the current along the line, and it's defined by the characteristic impedance of the line, which is related to the inductance and the capacitance parameters for that line. Then reflection, if there's any change in the impedance at any point in the line, like any discontinuity of some kind or a step. And this reflection can then cause standing waves. Then there's attenuation and distortion, where this involves the resistance and the conductance, which reduce the signal strength and can cause distortion over large distances. So where are these equations applied? The equations are used in the analysis and design of a lot of electrical systems, including the systems on chips and systems that are transmitting signals to the chips through the package, for instance. So high frequency signal transmission, that's a significant area in areas like data communication cables, telephone lines, RF circuits, and circuits associated with chips. Power transmission lines to model the propagation of electrical power over long distances. Of course, when the power coming to your house, that is long distance on a different scale than power coming to the chip, but the same concepts do apply here. And also with high-speed digital circuits, where the interconnects, that's the electrical lines, both on the chip as well as the lines coming on the motherboard, as well as the lines coming in the package to the chip, they behave like transmission lines, and they can affect the signal propagation, reflection, and attenuation. So looking at these, so what's going on here, right? So we're not going to go into too much detail. You just need to be aware of this. And in real life, what you will be doing is very likely using simulation software, or you will be interacting with an electrical engineer who will be using simulation software. So you don't need to know these in great detail, but just to understand what's going on, for those of you who do not have an electrical engineering background. So here's the unit, right, that we're modeling with a resistor, an inductor in series, a conductance, and a capacitance in parallel here. And here are the equations where first the slope of the voltage is a function of, so voltage is changing when you have a signal, so right? So the slope of the voltage will, like in a sine wave, you can see that the slope keeps changing, right? So just as the voltage changes, the current also changes. So the slope of the current over distance, each of these are related to these terms. So the slope of the voltage as a function of position is equal to, here's resistance plus J, there's a minus sign in front. J is the imaginary unit, right? That tells you that there's a phase shift, times omega, which is 2 pi over L or 2 pi F, which is related to the frequency of the signal coming in, multiplied by the inductance, multiplied by the current as a function of position. If you look at the second expression, the slope of the current as a function of position on the line is minus G, the conductance, plus the imaginary unit multiplied by 2 pi times the frequency, multiplied by the capacitance, multiplied by the voltage as a function of position. That's the first differentiation. The second one is the second d squared v. So this is, okay, so the first derivative, as you know, that's these, represents the slope or the rate of change of a function. The second derivative, right, when you differentiate a second time, d squared over dx squared of the voltage, represents the rate of change of the slope. So how fast is the slope changing, which is interpreted as a curvature or concavity of the function. In physical context, the second derivative often corresponds to an acceleration. So if the second derivative, that's this, is positive, so it's also represented as f single prime for single derivative, or the first derivative, and double prime for the second derivative. So f double prime x is greater than 0. That means the function is concave up. It's shaped like a cup upwards, meaning the slope is increasing as you move along the curve. If the second derivative is negative, so if this term is negative, f double x double prime x is less than 0, that means the function is concave down, meaning the slope is actually decreasing as you move along the x-axis. The solution of these equations is a wave, typically a sine or a cosine wave, or it could be an exponential function as well. So here they basically the equations are saying that the second derivative of the voltage as a function of position is equal to gamma square times the voltage as a function of position, and gamma is defined here. So we'll go down and look at this in a moment. The second derivative of the current as a function of position is equal to the same gamma squared multiplied by the current as a function of position. So these are general equations, and you solve them, and that gives you wave equations. So in this case, gamma is the propagation constant, which is equal to the square root of the resistance plus the imaginary unit multiplied by the frequency, 2 pi f, multiplied by the inductance, the entire thing multiplied by the conductance plus the imaginary unit multiplied by the frequency, 2 pi f, multiplied by the capacitance. And that can be represented as an imaginary number, where after you do all of this, you end up with an alpha, a number, plus the imaginary unit multiplied by beta, another number, where alpha is the attenuation constant, which basically means as alpha goes up, what happens is your signal is decaying in amplitude. And beta is a dispersion. The beta here is the wave number. It's a dispersion that happens when beta is dependent on frequency. And what that means is that as the frequency is higher or lower, the speed of that wave becomes faster or slower, depending. The characteristic impedance, Z0, is equal to the square root of the resistance for this unit, plus the imaginary unit times 2 pi times the frequency multiplied by the inductance divided by the conductance plus the imaginary unit multiplied by the frequency, 2 pi f multiplied by the capacitance. So the characteristic impedance makes a difference to the input that's coming into the circuit, and also in terms of trying to match the impedance to minimize reflections. Moving on to the next slide. Okay, so here, it's basically the same equations on the left that we've gone over and seeing what each of these things mean. The propagation constant gamma, that's this, describes how both the amplitude, that's the amplitude, and the phase of a signal change as it moves. It's a complex number consisting of an attenuation constant and a phase constant. So the attenuation constant we talked about, alpha, describes how much of the signal amplitude decreases as it travels along the transmission line because of losses due to resistance and dielectric leakage. The phase constant, or the wave number, that's beta, describes how the phase of the signal changes along the line related to the wavelength and frequency of the signal. the characteristic impedance Z0 or Z0, depending on what country you're from, the intrinsic impedance of the transmission line determines how voltage and current relate at each point on the line. It plays a key role in signal reflection and transmission behavior. Okay, so impedance discontinuity. So here on the right-hand side at the bottom, we see that there is a transmission line. It has a certain dimension, then suddenly there's a step, it gets wider, then there's another step, it gets smaller, then it gets even smaller, and then it comes back to the original size. So each of these steps results in a change in the impedance, the resistance, if you will, to AC of that metal line. As a result of that, every time there's a change, there's some kind of a reflection. So if you look at the amplitude, for instance, as a function of position, you will see that here's the incident amplitude. There's a reflection here, there's a drop, and then it jumps back up, goes through here, then there's a jump again here. So this is the impedance and it changes here as well. And once it ends, you have like a jump up here. So what you don't want are these kinds of steps, because these kinds of steps can cause reflection of signal, loss of signal, and so on. So signal energy is reflected when there is a discontinuity in the impedance, like we are seeing at each of these steps. And that's measured, if you will, or captured in this term gamma, capital gamma, which is the impedance L minus the characteristic impedance. So it's the local impedance minus the characteristic impedance of the line divided by the local plus the characteristic impedance of the line. So reflection is measured with scattering parameters in the frequency domain and with time domain reflectometry in the time domain. So we've seen this. So ZL is actually the load impedance. I misspoke. It's the impedance at the discontinuity. And Z0 is the characteristic impedance of the transmission line before the discontinuity. But it's basically the sudden change in impedance from here to there, right? So what is the physical meaning of gamma? Physical meaning, if gamma is equal to 0, you do all of this math and it turns out to be 0, there's no reflection. If gamma is, the modulus of gamma is 1, so if gamma ends up being +1 or -1, you have a complete reflection. All of the signal is reflected back to the source, nothing goes through. So this happens when ZL is either open circuit, infinite impedance, or short circuit, 0 impedance. In real cases, typically gamma will be somewhere between 0 and 1, which means partial reflection occurs, with some of the signal being transmitted and some of it being reflected. So you want to minimize the reflections. So you want to minimize such discontinuities. So the implications of the discontinuity is basically signal reflection that can result in standing waves. And there's also a loss of signal integrity for high-speed signals because it includes signal distortion, reduced bandwidth, and timing errors. If you slow down the signal at some part of the circuit and other parts is traveling faster, you'll end up with either a paucity, that is a gap in the signals, or a crowding together of the signals. And that either of those can cause errors in the operation of your circuit. So to minimize reflections, what you try to do is you try to ensure that you have impedance matching between the transmission line and the connected load or any components that are added in. This is particularly important for high frequency, high speed systems like RF circuits, Ethernet cables, high speed digital buses, like we see in the circuits that we're talking about. So the next slide, input impedance of a transmission line. The input impedance is the impedance that's seen at the input of a transmission line, and it's crucial for determining how a signal will propagate through the line, right? It's important to impedance matching, which is needed for maximum power transfer and minimum signal reflection. That input impedance, that's what do you see in terms of the resistance of the line, varies with the length of the resistance line, the load impedance, and the characteristic impedance of the line, which depends on it depends on the geometry and the materials that you've used. So if you have a mismatch in the input impedance, you'll end up, as I said, with signal reflections, standing waves, and signal degradation. So here, it's just an expression that you can look at. The input impedance is a function of length, is voltage as a function of length divided by the current as a function of length, which expands into this formula, where Z0 multiplied by 1 plus gamma, which we've talked about, exponent minus 2 gamma L divided by 1 minus the same expression. So we talked about this, that mismatch input impedance leads to signal reflections, standing waves, signal degradation. And there are specific configurations that people can use, like quarter wave transformers, to manipulate the input impedance for purposes of matching. For transmission lines that are lossy, which means that they lose some of the signal, the input impedance also reveals how the losses, resistance, and leakage affect signal propagation, which enables the designers to try to modify either the input or the output or the line itself to minimize the attenuation, the loss of signal, and any phase shifts. So here's an example of a strip line where there's a certain width, a certain height, and here's the metal line, and it's in a dielectric. And so here, in this case, Z0 is calculated by this formula we had mentioned previously, and that turns out to be square root of the inductance divided by the capacitance for high frequency or lossless scenarios, basically with low resistance, with resistance not be an issue. And the capacitance can be determined from this geometry as W multiplied by T multiplied by epsilon R, which is the relative permittivity of the dielectric constant, effectively, of the dielectric here, oxide or whatever, divided by H, where H is this height. So to increase the characteristic impedance, you basically target to decrease the capacitance by increasing the height. So you make this high, or you decrease the width, W, the thickness, and the dielectric constant. So increasing the characteristic impedance is beneficial for signal integrity, power efficiency, and impedance matching. Particularly important for high-frequency systems, RF radio frequency circuits, and compact printed circuit board designs, digital circuits. In those applications, minimizing reflections, power losses, and parasitic effects are important for good performance. So why do we want to increase the characteristic impedance? Benefits: reduce power loss, lower capacitance, better signal integrity, impedance matching, lower power consumption, compatibility with standard interfaces that require higher impedance, reduce dielectric losses in high-frequency applications, and space saving in the printed circuit board design because of the fact that you're using narrower, because one of the things that you do is you make the width of the lines narrower by narrow traces. So in summary, transmission lines are needed to provide electromagnetic wave propagation guidance for high frequency applications. The behavior of these lines can be characterized by their distributed components: resistance, inductance, capacitance, and conductance. Matching the impedance of the transmission line is critical to reduce reflections, signal reflections, and energy loss to ensure signal quality. And strip line that we saw is one of the most common planar transmission lines, and its performance can be tuned with the use of design rules and material selections. So here are some critical thinking questions for you to consider, to think about, that will expand your application of these concepts that we've talked about. How do the basic concepts of signal integrity, such as timing, noise, signal distortion, influence the overall performance of digital circuits? And why are these factors particularly important in high-speed designs? Second questions: in what ways can poor signal integrity lead to system malfunctions or data errors? And what proactive design strategies can you implement to ensure stable signal transmission? Third question: how do the physical properties of interconnects and materials in a circuit layout affect the signal integrity? And what role does careful component placement play in minimizing the signal degradation? Okay, so that ends this mini lecture. And I am going to go ahead to the second one. Okay, so I'm going to go ahead and share my screen. Okay, now I'm going to maximize my screen. Okay, so in this mini lecture, we are speaking about introduction to signal integrity. So here is a example of a server system and its topology. So here is a it's not a cross section, it's a top-down view. And this is the Think System ST550 server. So a server, as you know, is just basically a computer. It's just more powerful than your regular laptop, for instance. So when you look at the top, from the top down here, I'll point out the different components. To some of you, this will be things that you already know. For some of you, you don't know these, right? And that's fine. So over here, we have CPU 1, which stands for Central Processing Unit. That's basically the logic core. And there are 6 DIMMs. So around it are 6 memories. A DIMM is a dual inline memory module that's placed close to the CPU for the CPU to quickly access those memories. So here's one CPU. There's another CPU, a second CPU. So this server basically has 2 CPUs, central processing units, and that also has 6 DIMMs. That is the dual inline memory module here. You have various fans. A lot of these chips create a lot of heat, so you need to be able to remove the heat. So on the board here in the system or in the box, right? We're looking at like an aluminum box or whatever this is placed in. There's a fan, okay, a simple swap fan here. There were more fans. Okay, 3 simple swap fans placed here. Then you have the 5.25 drive base in this case. So like whatever it is, like optical disk or floppy drive or USB nowadays, right? Uh, or they could be like a flash drive that has no rotating disk. Here is a serial port header. What is that? Serial port header is an interface to connect external drives. So you can plug in external drives to your system here. Then we have a PCIe here. We've got 6 slots, PCIe slots. What are they? They're peripheral component interface express slots. What that means is you can connect in peripheral components, whatever, whether it's a laptop or a mouse or other kinds of components. Then down here, we basically have a TCM port, and this says this is basically in China. The TCM port is basically a tightly coupled memory port. So you can put in a memory that's tightly coupled to the system. Then over here, we have an M2 adapter slot. What is that? The M2 adapter slot is basically for internal expansion cards, which means you can put additional cards that have additional functionality, whether it's memory or something else there. Then over here, we have 2 SATA, right, for ODD. Let's see what that is. SATA is Serial Advanced Technology Attachment. So it's a communication protocol plus the hardware. So these are standardized. So any manufacturer who creates any device that uses that communication protocol, it's like choosing a language, right? Like if you say that you're going to speak whatever English, no matter what country we're from, we're able to interact with each other as long as we both know English. So things like SATA and so on, these different protocols are intended to make it so that the server can communicate with devices that are made anywhere in the world, as long as they use that language, that protocol for communication. ODD stands for optical disk drive, which means that you can plug in an optical disk drive here to the server. Then further down here is that should be USB, not D. USB 3.0 for RDX. So USB is Universal Serial Bus. Again, that's the hardware as well as the protocol for communication. RDX is for removal disk storage, where you can plug in a disk or take it out, or plug in a thumb drive and take it out. Here we see 2x 6 gigabyte SATA ports, and GB is basically gigabyte, and a giga is a billion bytes, and a byte, as you know, is 8 bits, right? So this is a billion 8-bit bandwidth communication. HDD here are HDD drive bays, where you can plug in hard disk drives into this. So that gives you an overview of the system. So everything that we're talking about, the packages and so on, are here, and the chip will communicate through the package to the connectors to the motherboard, which will be a printed circuit board on which you put other chips and all these other peripheral components. And around that, we have fans and we have additional drives. We then talk to the motherboard so that we can communicate from the chip to the drive and from the drive to the chip. So that's an overview. So here I just expanded the image, and I'm making the point that various I/O input-output links are available for IC integrated circuit chip components to communicate. And those different protocols, the different forms of communication, have different speeds. Reach, which is the distance that the signal can move without degrading. Latency is a slowdown in the signal because of the resistance and leakage and all kind of stuff, and reflection, all that kind of stuff. And density. So density would be how many bits, for instance, you're getting per second, or bytes per second. So here's a schematic of that, what we saw. You can see here in this case, it's the same ST550 system architecture block diagram, thanks to Intel for this. So here there's an Intel Xeon CPU 1 chip. Here is a second CPU. Here is a C624 from Intel. It's a PCH chip. And then there's an XCC chip. And then here we have DDR. So let's look at these. So this is schematic. The DDR are dual data rate memories. So each of these is a memory chip. It's talking to the CPU, which is the central processing unit. So here are more of the dual data rate memories. Here's the second chip. Then UPI is a communication protocol and hardware that can talk between chips. Then we have a slot for PCIe, and here that's peripheral component interface express. So you can plug in, there are different things that you can plug into these slots. There's an M2 slot that we talked about for internal expansion cards, PCIe and SATA protocols for communication to the PCH chip, and PCH is Platform Control Hub chip. And that you can see is getting signals from the central processing unit from here, for instance. And then that can communicate SATA to an optical ODD as an optical disk drive. And it can also communicate to a 6 gigabit SATA to other devices, right? And then over here, it's basically making the point that you can have RAID and NVMe. NVMe is non-volatile memory, additional memory on additional printed circuit boards that you can plug in. And RAID is a system, it's a redundant system of independent disks. It's a way of protecting your data. If one disk crashes, you have it copied on multiple disks, so that if any one crashes, you still have data that's spread among the other disks. So I think that covers the key things. So ODD, we said, was optical disk drive, and that's basically it. So this CPU is also talking to memory here, and it's talking to PCIe slots. So you can have other devices that then communicate to this. So that's the architecture of the 550 server. Okay, so again, the point with this is that various input-output links for the IC components communicate. So there's everywhere there's a line, there's communication. So different colors. There's red communication, blue communication, over here, black communication, orange communication, and red communication there. And each of those can be different speeds. It can different speeds, different reach distances, different latency, slow down or speed up compared to each other of the signal, and density of the signals coming in. All of that needs to be taken into consideration when you're designing your chip, your package, your motherboard, and the system as a whole. And so these are basically the figures that I had on the previous slides, making the same point. Moving on. So if we look at the channel building blocks, here is a cross section. Is a cross section of the green at the bottom is the printed circuit board. Above that, you have either sockets or ball grid array connection between the motherboard, the printed circuit board, and the package. And then your connection from the package to the die, which could be solder bumps, right? Or so here, if you expand this, the bottom of the die where it talks to the package, you can see a configuration like this, where you have what's called C4 bumps. Those are control collapse solder bumps, and routing that comes away, that is metal lines, interconnects that come to a pad that the bump is on, and then take the signal to wherever you want it, or the power wherever you want it. So if you look at the package here, so here is an example of the routing on the package. So you have a whole bunch of different lines transmitted that are built into the package, either on the surface of the package or buried inside the package in one or more layers that then come up to vias that go up to the die. So you can see this is pretty complicated. And so every single one of these is a form of a transmission line. So you have to be able to simulate and understand with this configuration what is the behavior of the signals or the power that's coming in any of these lines. And in a previous lecture, one of the students had a question about the interaction between power lines and signal lines. And that was an excellent question. It is an excellent question. That's something you have to build into this as well. You have to put your power lines, you have to keep them away from any very sensitive signals, and you have to make sure there's enough spacing between them to make sure that you don't degrade the signals. So this is the package substrate routing. Now here we have a DIMM board. There's a plug-in connector, DIMM connector, and then the board is plugged in vertically. And the board contains a memory chip or chips and a package. So again, there's a chip, there's a package, there's the board, and that's plugged in here into this. This is a dual inline memory module. So this is the top side of the chip. Now looking at the motherboard itself, right? Here, now here we have routing associated with the motherboard because we have signals that will be coming in here, going to the motherboard, and signals coming from the chip going through the motherboard to the memory, and so on. And so here is an example where you have lines of different shapes, and then the circular dots are basically posts or vias that are going through the motherboard or through a layer in the motherboard. And with all of this, you have to model all of this to make sure you don't have signal issues. So that was the top. Looking at the bottom of the board. So in the previous slides, we looked at the top. Now, when we look at the bottom, here we can see we have substrate vias and sockets to communicate from the bottom. So you can see there's a line that's coming down here that talks to there can be sockets, there can be vias, and these are motherboard vias through the motherboard. There are also substrate vias and so on coming down from the package down to the motherboard and so on. And then here we have memory contacts between the motherboard and the memory modules. So each I/O signal needs to travel through a pretty complicated path consisting of high density traces, that means interconnect lines, vias, connectors, and solder balls. So all of that needs to be modeled and controlled and designed well. And then the process that you use to create the physical component needs to match the structures that you put into the resistance values, the inductance values that you put into your simulation. So it's a very complex process. So that C4, so we've seen this before with those are the different parts. Okay, moving on. So communication, as you know, is not easy. There are lots of opportunities for misunderstanding in human communication. The same thing with communication on a chip. So on the chip or any device, we have an input data stream. So you're looking at the voltage on the y-axis here versus, let's say, the clock signal or time. And you can see that there's a square pulse, the blue pulse here, nothing, and then a square pulse, nothing. So this would be the equivalent of saying 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, with each of these clock ticks, if you will. That is the input coming in through your transmission line that you're putting into your transmission line, for instance. And it turns out that when you look at the signal at the end of the transmission line, that square pulse has become degraded into this kind of curve. And this degradation occurs because of losses, reflections, crosstalk, and noise in the channel. And we talked about some of the causes of those. Signal quality will degrade when traveling over the I/O, input-output physical media, resulting in a loss of amplitude and sharp transition edges. The transition edges get blunted. So you can see that this sharp edge here got blunted here, and the peak has come down. And then there's a long tail. So where there's supposed to be zeros, it turns out that there is some signal. Where there's supposed to be a 1, you're really getting like probably a 0.6 or so. So same thing with the next signal, same thing with the next signal. Notice the gap between these two signals. There's supposed to be a 0. Instead of a 0, this tail from the first signal is overlapping, or rather the tail from the second signal is overlapping the front edge of the third signal, resulting in a number here that's about 1/3 of the height. So all of this has to be taken into account so that your computer has to be careful to not read any of these as zeros and not read this as a 1 or this as a 1. So signal quality degrades when traveling over the I/O. Physical media, it loses amplitude. We see that where the blue peak drops to the red level and sharp transition edges. So this means that you are limited in how long the transmission lines can be depending on the transmission line. And if it turns out that you do need a longer line, then you have to design that line in such a way that it minimizes this degradation. So here's a picture of an IBM PC from 1981. You can see what a mess it looks. There's a whole bunch of chips on it. And the chips are a combination of logic chips as well as memory chips and then connectors. So here are the ISA. ISA at that time was industry standard architecture bus, and it operated at 4.7 megahertz. And so you could plug in other components into these locations and communicate with them using this hardware and communication protocol. And here is a picture of an Intel 8088 chip. And you can see on this chip, it basically has, you can see that it has these posts or legs on one side, it has it on the other side, but nothing on the third and the fourth sides. So this is basically a dual inline configuration. And you can see there are not very many connectors, right? So if this number is whatever, like say 20, there's a total of maybe 50 connectors. That's it. Modern chips need much more than 50 connections to the chip. They can need anywhere. We have seen the numbers can be 1,000, 2,000, 4,000, depending on the chip. So going to the more recent generations, there's a speed increasing that's approaching 10,000 times faster than this chip. And that increases the risk of signal integrity issues. So here are all those components together: the IBM PC, the Intel chip, the ISA communication slots. And moving on, the more recent boards from 2022 was the Intel Xeon server with the PCIe 5th generation configuration operating at 32 gigabits per second. So that's 32 billion bits per second. And speed increase from the previous to this is about more than 10,000 times. So the risk of signal integrity issues increases as a result. So signal integrity. Signal integrity is a set of measures of the quality of an electrical signal. The challenges of ensuring signal integrity or quality increase as you increase the signaling speed, the travel distance, the signal density, and the complexity of the material that you use to make the transmission line and the materials around it. So there are electrical engineers and process engineers and chemical engineers who work together as teams to address these issues. Signal integrity engineers are responsible for analyzing signal propagation to achieve better channel metrics, bandwidth, latency, power efficiency, and to avoid system performance degradation or failure. So it's 6:25 now. We started at 5:30. So let's take a 5-minute break and then we'll come back. Okay?
Okay, Professor.
Okay. Yeah, take a 5-minute break. We'll be back. Let's say it's 6:26 now. So let's make it 31, 5:31, or whatever your time is plus at 31. So for me, it would be 6:31. Okay, ladies and gentlemen, let's go ahead and start. $631 here. As soon as it changes to 632, I'll start. Okay, it's changed to 632. So I'm going to minimize the Zoom little window and maximize my screen. Okay, so we talked about this screen. And we talked about the fact that signal integrity engineers analyze signal propagation to achieve better channel metrics in terms of bandwidth, latency, and power efficiency. Doing so enables them to avoid system performance degradation or failure. Okay, admitting a student. Okay, so here is an example. This is in terms of system level metrics. Input-output channels can be quantitatively described with the bandwidth, abbreviated BW for bandwidth, measured in gigabytes. Capital B is byte, that's 8 bits per second. Giga, as you know, is a billion. So a billion bytes per second. This is the amount of data transfer per second between two communication building blocks. So one component and another component communicating at that rate. This is a function of the signaling rate, RS, and the bus width, W. Signaling rate is in gigabits per second, so how much bits you're sending through per second in one line. And bus width is a measure of the number of lines that you have. You can have 2 lines, 4 lines, 8 lines, 16 lines, 64 lines, and so on. So the bandwidth in gigabytes per second is proportional to the signaling rate multiplied by the bus width. And here is an example. 5th generation DDR, that is double data rate DRAM, dynamic random access memory, the channel communication. In this case, the signaling rate, RS, is 6.4 billion, so gigabits, billion bits per second. The width is 64 for the data bus. What that means is there are 64 lines that effectively 64 lines are bundled together to be able to communicate the data so that you have 64 bits that can transfer in parallel. So given these two, the bandwidth is 6.4 gigabits per second multiplied by 64 multiplied by 1/8 to translate between a byte and a bit gives you 51 gigabytes per second. So bandwidth is equal to rate multiplied by the channel width or the bus width. Latency is the slowdown in the signal, L, in nanoseconds. A nanosecond is 10 to the power of -9 seconds. So it's 1/1000th of a second. Latency is the time that it takes between generation of a signal at one building block. So you generate the signal, and how long does it take for its reception at the other building block of the circuit? And this is a function of transmitter-receiver circuits, the circuit, and the signal travel time on the physical interconnect. So the latency L is equal to the circuit latency. There's some slowdown in the signal because of the response time of the circuit, and the interconnect latency. And that's the slowing down of the signal because of resistance and all that sort of stuff that we have talked about. So Li, which is the interconnect latency, is the length of the connector divided by the velocity of the wave or the signal in the connector. So here, V is the speed of light if we are talking about light. But electrons, as you know, signals don't transfer at the speed of light. So here is an example, an ultra-path interconnect, the UPI routing. This is the connection, the signals, or rather it's the interconnects between one logic chip, central processing unit, and another CPU chip. In the case of a 10-inch UPI routing on the motherboard, the latency due to the interconnect is the length, which is 10 inches, multiplied by a conversion factor to convert to meters, divided by the velocity. In this case, the signal velocity is 1.5 times 10 to the 8 power of 8 meters per second. And this conversion factor is converting from seconds to nanoseconds. So 1 times 10 to the power of minus 9. So multiplying and dividing gives you 1.69 nanoseconds. That's the latency, which means the signal, by the time it comes from the circuit, it's moved through this 10-inch routing line. It has slowed down by 1.69 nanoseconds. So you have to take that into account to make sure that you don't have signal propagation, signal recognition errors. Another system level metric is the I/O, input output power efficiency, PE, measured in milliwatts per gigabit per second, or in pico. Pico is 10 to the power of minus 12 joules per bit. This is the amount of energy it takes to generate 1 bit of data at one building block and transfer and receive it at the other building block on the circuit or on the board or in the package. This impacts the total I/O, input output power, P, in watts. So the power P is proportional to the power efficiency PE multiplied by the bandwidth, BW. So in an example here, for a high performance computing cluster, HPC cluster that has 1,000 processors, so 1,000 chips, for instance, where each processor needs 1 terabyte per second. So a gigabyte is a billion bytes per second. A terabyte is a trillion, 1,000 billion bytes per second bandwidth. What should the PE be? That's the power efficiency to keep the total memory input output power less than 50,000 watts. That's a lot of power. So when we do the math, it turns out that the power efficiency is equal to the power divided by the bandwidth, power divided by bandwidth. So power is given to us at 50,000 watts. So you're multiplying that by 1e6, that's 1 times 10 to the power of 6, a million to convert to milliwatts per kilowatt, dividing by 1,000, because we have 1,000 processors, multiplied by 1 terabyte per second, multiplied by a conversion factor to go to gigabytes from terabyte, 1,000 gigabytes per terabyte, multiplied by 8 bits per byte, and that gives us 6.25 milliwatts per gigabit per second, or 6.25 picojoules per bit. In addition to this, there are other metrics such as jitter, which is the lateral translation of your signal, and the bit error rate. So the rate, if you send 100 bits through, how many of them come through correctly? These are used in system level signal integrity analyses. So we have seen this, just reminding us of the configuration of the server. And here are the types of IOs, the speed, the reach of the IO. That's how far can this particular form of transmission occur without too much degradation of the signal, the latency here, and the density. So die to die in a multi-chip package, the speed is a few billion bits per second, few gigabits, bips, gigabit per second. The reach is a few millimeters. That's how far you can keep the dies apart. Latency is a couple of picoseconds. So these interconnects can slow down your signal by a couple of picoseconds, 10 to the power of minus 12 seconds. The density can be hundreds of these connections per millimeter. A chassis level IO, that's the chassis, the metal box, whatever, on which you put the boards to build your computer with. So you can think of this like motherboard level. For the memories, PCIe and UPI, the different interconnects that we've talked about, the speed is a few to 10 gigabits per second. The reach is a few inches. Latency is tens of picoseconds. So these are slower than the ones on the die-to-die. And the density is a few tens per millimeter. For a long reach connection, right, for a switches, for instance, you could have 10 to hundreds of gigabits per second. the distance for optical reach without degradation of signal can be a few meters to kilometers. The latency is a few to tens of picoseconds, and density is a few of these per millimeter. So just as a reminder, a picosecond is 10 to the power of minus 12 seconds. So package layout, we're now moving to the foundations of electromagnetism. I'm not able to see the top of my screen because of the Zoom notification. But so here's the layout of the package. Here's the chip location, if you will. And for each of these lines, if you look at like the blue line, the red line, if you look at any of these lines, interconnect lines, in the case of a microstrip or a strip line, in the case of a strip line, here's a metal line that's coming perpendicular to the plane of this micrograph, this image, traveling perpendicular to the plane. That's a metal line, the black thing. And then around this is a dielectric, and this is completely locked inside dielectric. Whereas in the case of a microstrip, you've got the dielectric down here and then the metal, and then the top is exposed. So here, the electric field lines are the solid lines. You can see the solid lines based on the voltages that are present. And here also you see the solid lines, and you can see the electric field is limited, if you will, because of the material configuration. Whereas in the microstrip, the electric field extends further out. And then the magnetic field are the dashed lines. The dashed lines in the microstrip, you can see they extend out further, whereas in the strip line, it's more compact. And this makes a difference to if you have another line that's near this, the magnetic field of this strip line, microstrip, can interact with the magnetic field of the other one and create a signal in it. And you don't want that. Similarly with the electric field and so on. So now we are moving to you don't need to understand all of this. Of course, if you're an electrical engineer, you already do or need to understand it. But for the rest of us, for the rest of the students, I'm just giving you an overview. You don't need to understand this in great detail, but these are the equations and the understandings that go into the software that is used to simulate transmission line behavior, for instance. So the first law is Gauss's law. And so the equation, there's a differential form for those of you who have taken calculus, which I'm assuming is all of you, and an integral form. So the differential form basically says del is an operator, dot d, and we'll talk about each of these items, is equal to rho. The integral form says that the surface integral of d dA is equal to the volume integral of rho dV. So what do these things mean? Okay, physically, what these things mean is that charges create electric fields. And Gauss's law, that's this, describes how much electric field flux passes through a surface depending on how much charge is inside that surface. The electric flux is proportional to the enclosed charge, meaning the more charge you put inside the surface, the more the electric field lines there are that pass through the surface. And this helps us also to simplify calculations of electric fields in symmetrical situations and shows that the electric field behaves in predictable ways based on the charge distribution. So what are these things that we are seeing here? Del dot D, that's this, is the divergence of the electric field, how the field diverges from a point. D is the electric field flux density. It's proportional to the electric charge that's inside. So if you think of the electric field lines coming out, what's the density of those per unit area, for instance? Rho here is the electric charge density. A is the area. V is the volume. And yeah, okay, there's no E here, so I'm going to ignore that. But the E would be the electric field, which would be the force per unit charge at each point in space. D, as I mentioned, is the electric flux density. And in the material, it's proportional to the polarization field. And this is the case without a polarization field. The next equation that's used in electromagnetism is Gauss's law for magnetism. So we have a similar structure here where del dot B in this case is B is the magnetic field, del is an operator, A is the area. So the differential form, the integral form, differential form del dot D is B is equal to 0. And we'll talk about what it means physically. The integral form is the surface integral over surface of B, which is the magnetic field, dA over the surface is equal to 0. So what does this mean physically? What it means is there are no magnetic monopoles. That is, when we have a north pole, you have to have somewhere near it a south pole. Gauss's law for magnetism implies that magnetic monopoles, that's an isolated north pole or a south pole, does not exist. Magnetic fields are also always generated by dipoles, north pole, south pole, or by a current. And magnetic field lines must form closed loops. So here, magnetic field lines are closed loops. A field line never starts and stops suddenly. It always has to loop back on itself. For any closed surface, the magnetic field entering is equal to the magnetic field that's exiting, resulting in a zero net magnetic flux. This then leads us to conservation of field lines. The law reinforces the idea that magnetic field lines are conserved in nature. They do not have singular sources or sinks like electric charges. You can have a positive charge and it sends out, right, the electric field lines. Whereas you cannot have just a North Pole magnetic. We next move to Faraday's law of induction, which basically states that, again, the same del operator, del cross E is equal to minus the slope of B over T. So what are these things? B is the magnetic field. E is the electric field that we see here and here. L is length. Where is L? There. L is length. T is time over here. A is the area for the surface integral here. So del cross E is the curl. What is curl? Curl is the way the electric field curls around a point. So if a point, the electric field curls around it. So how does it curl? And this del cross E is basically telling us about the nature of the curling. dB over dt is the time rate of change, the slope of B as a function of time, the magnetic field. So if the magnetic field changes, it has effects. So that's the differential form. The integral form is that the surface integral of the electric field, I'm sorry, it's not a surface, it's a linear integral of a closed path of the electric field over a closed path is equal to minus the area integral over the area of dB over dt, which is the slope of the magnetic field as a function of time, how it's changing with time. What does this mean physically? What it means physically is the law is explaining how a changing magnetic field induces an electric field. So if you have a wire here and you change the magnetic field, that will induce a current in, it induces an electric field in the wire. And this is what lets us generate electricity. It shows that electric and magnetic fields are fundamentally linked. A changing magnetic field creates an electric field. And this is the basis of most electrical technologies. The induced voltage opposes the change in magnetic flux, which means that if the flux is changing like this, then what happens is there's a voltage, an electric field that's induced in the conductor that opposes this change in the magnetic field. That's Lenz's law, maintaining conservation of energy in the system. And the fourth and last one here is Ampere's circuit law. And let's look at the items. There's a del operator, which we have seen. There's H. And what is H? It's the magnetic field intensity or the magnetic field strength. We've got a J, which should be the current per unit area. So it's a current density. We've got D, which is the electric field flux density over T, time. And we have the same quantities here. In the differential form, del cross H, which is basically the curl of the magnetic field intensity. So how the magnetic field curls around an electric current. If you have an electric current going like this, there's a magnetic field that curls around it. So that's what this is referring to. Around an electric current or a time-varying electric field. That is equal to the current density, current per unit area, plus the rate of change of d over capital D over dt is the time rate of change of the electric flux density. So there are two different components of electric behavior that contribute to the magnetic field. That's the differential form. The integral form basically says that the integration over a closed path of H, which is the magnetic field intensity, or with dl, closed path, should be equal to the area integral of J plus dd over dt. So that is the area integral of the current density here plus the electric field density, its variance with time, integrated over the area. So what does all this mean physically? These are just the equations, right? But what do they mean physically? What they mean physically is here. Currents produce magnetic fields. Ampere's law tells us that electrical currents generate magnetic fields that circulate around the current carrying conductor. Magnetic field strength is proportional to the current. The greater the current, the stronger the magnetic field. Magnetic fields form closed loops. The magnetic field lines always form closed loops around currents and do not start or stop like electrical field lines. The integral form that's here shows the total magnetic field. The sum of the magnetic field around a loop is directly related to the current that's enclosed, the electrical current enclosed by that loop. So this page is basically Maxwell's equations, right? And they summarize all of these. And so Maxwell's equations are the governing equations for electromagnetic fields as the foundation of signal integrity analysis. So if you're a signal integrity engineer or an electrical engineer in this field, you would be applying this in your simulations. And most of this will be done with software, where these equations or the equivalents are built into the software to figure out the electric fields and the magnetic fields and the interactions between different lines and so on. So that's the basis. So summary of this, signals between electronic components need to travel over complicated environments. We've seen some pretty complex layouts, and they will degrade significantly if you're not careful. The signal speed, as it increases, right, as we come to newer and newer technologies, there's a significant increase in the speed. That drives a greater focus on signal integrity to ensure signal quality, propagation quality, and system performance. Signal quality is evaluated by multiple system metrics such as speed, latency, power efficiency. The foundation of signal integrity analysis is electromagnetic theory and solving Maxwell's equations for the specific geometries that are on your motherboard, in your package, and on your die. You can have an excellent chip, excellent like a logic chip, but if your package is screwed up, your entire system will not perform well. So we are definitely at the level where packages are very critical to maintain the benefits that we get from the advanced chips. Okay, so critical thinking for you to think about to expand your understanding. How do the fundamental principles of transmission line theory help in understanding the behavior of signals in high frequency circuits? And what specific factors must be considered to maintain signal integrity? Second question, in what ways does impedance matching in transmission lines influence signal propagation? And how would improper impedance management affect the performance of high frequency systems? So we have discussed enough things for you to be able to answer these questions, and you can always research this and go into more depth. How do losses and distortions in transmission lines affect high frequency signal propagation? And what design strategies can be implemented to mitigate, to make less bad, these issues in advanced electronic systems? So that ends this mini lecture, and we will go on to the third one now. Okay, I'll have to check to see if I am. Okay, I'll share my screen and then maximize my screen. Okay, so now we're talking about signal integrity analysis. So signal integrity analysis can be done at the component level or at the system level, and there's a need for both. So component level, we've got 2D, two-dimensional electromagnetic analysis, and that applies to uniform transmission line models. And we have three-dimensional electromagnetic analysis that applies to packages, printed circuit board vias, connectors, and non-uniform trace models. That's where the traces are changing shape, width, that kind of thing. System level, we use channel circuit analysis, where we look at things like channel timing and voltage margins and bit error rate. That's where you send in 100 bits of information and you see what percentage of those made it through correctly. Both component and system level simulations can include design of experiments, where you do a lot of experiments and integrate the data, and Monte Carlo analysis. Monte Carlo analysis is where you take a certain collection of parameters and you vary them at random in different random combinations to generate a whole bunch of in principle experiments. Like you can generate 1 million data points using a computer. And those 1 million data points are relevant if your software system is calibrated to the physical world. Just generating Monte Carlo without such calibration will give you nonsense results that they don't correlate with the real world. So it's important to calibrate the two. And that's done to capture variations from design targets. So an example, all of this is implemented typically in software, component numeric solvers. So what you do is you take a component and you split it up into little segments and you model that in a computer using something like different methods. So here are some examples where an integral equation solver software uses method of moments, which is a particular method that is used for the solving of integral equations for different configurations. And differential equation solver, you can use the finite difference time domain method or the finite element method. And again, those are different methods of taking a component that has a certain shape and then putting in the different material parameters and the different shape parameters, and then trying to figure out what happens to the currents, the signals, the magnetic fields, the electric fields, and so on, and how those fields interact between, for instance, this yellow line and the blue line here. So components with arbitrary geometry require discretization of the solution space into grids. This is the solution space here, into grids, and solving Maxwell's equations in each grid. So most of what we see in packages and chips are too complex for us to just set up the equations and solve the equations. The equations work for simple symmetrical situations. In real life, most of the time, we have to do some form of finite element modeling, where we divide up the chip into a bunch of little finite domains, solve the electrical and the magnetic interactions for a small domain, then use that as the input for the next domain, and then solve it there, then use that result as the input for the next domain, and do that 3-dimensionally. That's why, and really 4-dimensionally over time. That's why this gets to be so complex. So something that's important, the S parameters are the scattering parameters. So the numeric solver solution around circuit terminals for a linear network can be represented by scattering parameters called S parameters to describe its electrical behavior under various steady state stimuli, plural, by electrical signals. So here is an instance where you got an N port, that is N input-output network. You got input I1, which is a current coming in. Then there's a voltage. There is a current N1, N-1, voltage N-1. So here we've got signals coming in and going out, and a whole bunch of them. So you've got N, some number of, like, it can be 1,000 signals. And then we got, so this is operating as a black box. And outside this, we have I2 signals, V2 signals, and I1, 2, 3, 4, 5, 6, 7, up to N, which can be 10 or 1,000, whatever, signals coming out. And you got the input and the output there as well. So this can be used to interface with something like this, or to simulate the kind of layouts that we have talked about, right? So here we see the solder balls and the interconnects coming down to the solder balls and so on. And so using software, what we do is we simulate the return loss and the insertion loss, the crosstalk and near end crosstalk and the far end crosstalk. And all of this means that we're doing this for one particular cell or element. So S11 is the return loss scattering factor for the XY cell, where it's just 1, 1. And that is like related to B1 divided by A1, where we are looking. So in this case, we're looking at return loss. So A1 is the signal intensity coming in. B1 is the signal intensity coming out. Divide one by the other, and that gives you a measure of the loss. And insertion loss in this case would be B2 divided by A1. So you got A1 coming in. So how much of this is successfully making it through? So B2 divided by A1 tells you how much effectively is being 1 minus that, really. How much of that is being lost in insertion. And return is how much of B1 divided by A1 tells you how much is reflecting and coming out. Near end crosstalk is basically where you got crosstalk between two different lines, Bn minus 1 divided by A1. So you got Bn minus 1 coming out, we got A1 coming in. So this is telling us how much is A1 affecting the number coming out. Far end will be what's happening at the other end. So we are looking at Bn, how much is going out over A1. So if we keep all these other things 0, there's no inputs coming everywhere else, but you send in an A1, it turns out we do get some kind of a Bn, which is a measure. It's telling us that this line is cross-talking. It's sending in signals to this other line that we do not want. So that's the kind of thing that you have to do in signal pairs and optimize maybe the geometry or the materials to avoid that. So 2D electromagnetic analysis, the input here is a cross-sectional geometry like this. We've already seen this is where you got a metal line, then a dielectric layer, like an oxide, then the substrate. You have to input the material properties for each of these components and the frequency range. You put it into a two-dimensional electromagnetic mesh solver, computer software that gives you an output that looks like this, which tells you the resistance, the inductance, the conductance, the capacitance, the characteristic inductance, the reflection parameters as a function of length. And this is a cross section that's telling you with any one of these. So you could look at like the electric fields or the magnetic fields as a function of position in the line. And you can see that in this case, the fields are the strongest close to this line, and they get weaker as you go further out. And this tells you if these fields are strong enough to interact with another line that's placed here. So uniform cross-section components such as transmission lines can be analyzed by solving Maxwell's equations with a 2D, two-dimensional electromagnetic analysis tool, and that's very fast in computational time. Per unit length circuit parameters like the resistance, inductance, conductance, capacitance, and the characteristic impedance, Z0, and the length-dependent reflection parameters or the scattering parameters can be calculated using two-dimensional electromagnetic analysis. Going to the next level of complexity, now we're talking about three-dimensional electromagnetic analysis. So the input here is three-dimensional geometries, material properties, and the frequency range. You have a three-dimensional electromagnetic mesh and solver, which is the software. And that gives you an output of the S parameters, that's the scattering parameters, time domain impedance, and crosstalk profiles. And here's one way of representing it, where the different colors are different intensities of whatever parameter you're looking at. It could be like the fields and things like that, the electric fields, the magnetic fields, and so on, as a function of position superlaid on a schematic of the structure of the materials that you put in. So in this case, three-dimensional electromagnetic analysis is used to solve Maxwell's equations to calculate electromagnetic wave propagation through arbitrarily shaped objects. So return loss, insertion loss, and crosstalk characteristics for package and board vias, connectors, and sockets can be calculated using three-dimensional electromagnetic analysis using software and so on, such as this ANSYS, the company HFSS. So moving on then to system level circuit analysis. So here we have a driver. Here is your C4 bumps, right? The control collapse bumps. There's routing. So we're talking about the package, the plated through holes and the sockets going to a motherboard, breakout, motherboard, motherboard, motherboard main, motherboard via, motherboard break-in to a DIMM. So what's an SO DIMM? SODIMM is a small outline dual inline memory module. So it's a memory module. And then there's a transmission line out, resistance, series resistance, transmission line, then another transmission line, and then it splits into two transmission lines, then talking to SDRAM. And SDRAM is synchronous DRAM, where DRAM is dynamic RAM and RAM is random access memory. So you put in a signal and it goes through the system and comes out and you measure it. And as the signal changes, you plot a series of the signals, the zeros and the ones, and you get something called an eye diagram that we will talk about. The component models from 2D and 3D solvers are cascaded, right? So the models for each of these components, you have to create a model for every component, and then you have to take the signal input to this component, create an output, take that output and put it as input to this model, and that gives you an output, take that output, put it into the input. So you have to do this cascade. You have to cascade this in a circuit simulator like SPICE to obtain channel performance metrics such as eye margins, that's the eye diagram, which we'll talk about, bit error rate that we have mentioned, and unified power models. So construction of the eye diagram. Here's what you do. You have a transmitter that's sending a transition from a 0 to 1. So a 0 jumps to a 1. Then another transition is a 1 jumps to a 0, right here. And then we have a 0 transitioning to a 1, then a 0. So 0 becomes a 1, then a 0. Then another one is a 1 goes to a 0, then to a 1. That's this. And then what you do is you look at the signal at the receiver. So you got this input signal and that changes, right? So instead of being sharp, it has kind of curved and shifted a little bit. This step down signal has curved here. This step up and then step down has become this shape. This step down and then step up has become this shape. So what you do is you overlay all of these signals and you end up with something like this, where all the signals are overlaid onto each other, and you end up with what looks like an eye, like here, like the human eye. And here, from here to here is the eye height, here to here is the eye width. You do this with thousands of signals, and so you don't get a single line, you get all of these lines with jitter is this crossover point shifting from left to right for different signals. Rise time is the time that it takes for this signal to go up. That's the eye width is the distance from this crossover to this crossover. We talked about the eye height, the eye crossing, right? So the percentage is like, where is this crossover happening? So this is the 0 level, that's the 1 level. And this is the amplitude from 0 to 1. So and this is the bit period from here to here, where you're trying to switch your signal from 0 to 1 and vice versa. So the eye height measures the vertical opening of the eye diagram. It determines the closure of the eye. You need a big opening to prevent mischaracterization of a 0 as a 1 or vice versa. So this arises, the closing of the eye is an indication of low quality signal transmission in your circuit or system, and that is because of noise. The eye width is the horizontal width. Jitter in the system reduces the eye width, and you don't want to reduce that eye width again because you don't want to mix up a 0 with a 1 from a previous signal. Bit error rate is the percentage of the bits with errors divided by the total number of bits over a given period of time. So the target is something like 1 times 10 to the power of minus 10 or less, for instance, which is a very low error rate, as you know. In addition to this, okay, we have NRZ for 2 levels, PAM for 4 levels for increasing the bandwidth. So let's see what these things are. Pulse amplitude modulation, PAM, allows more data bits within a given data period if time to allow either an increase in the total effective speed or transmitting the same amount of data with lower frequency requirement of the system building block. NRZ is non-return to zero. So these are two different ways of trying to enhance your systems, their operation, their performance. Non-return to zero is where you're using +1 and -1 instead of 1 and 0. So here, m equals 2. So this would be, right, so this is talking about PAM. So in the case of PAM, which is pulse amplitude modulation, in a conventional system, you just have 2 levels, right? You got 0 and 1, 0 and 1. In PAM, what you can do is you're combining these zeros and sending them together. So instead of sending 0 and 1, you're sending 0, 0, 1, 0, 0, 1, 1, 0, and 1, 1. And you can do this in one wire. So here we're using one wire to send single bit at a time, whereas here we're using one wire to send dual 2 bits at a time. And the signal would look like this. For 0, 0, it's down here. For 1, 0, it's like 2 steps up. For 0, 1, it's 1 step up. For 1, 0, it's again 2 steps up. And for 1, 1, it's 3 steps up now. So that means you need to be able to distinguish in your circuitry between this level, this level, this level, and this level. So you need to have 4-state discrimination, right? And so there are ways of testing this to make sure you look at the spectrum for non-return to zero versus spam, and you look at plots like this, the decibels, which is the measure of the amplitude versus frequency, and you want to make sure that there isn't degradation of these as you go to higher frequencies. Okay, design of experiment is significant in the context of manufacturing of both the dies as well as the packages. So design of experiments, DOE, DOE experiments analysis considers manufacturing variations and material variations and enables system pass or failure judgment on a statistical basis in conjunction with Monte Carlo analysis. So here's the system that we saw before. You got the driver, you're sending in a signal that goes through all of these different parts of the system and comes out, you measure that, and then you do the eye diagram and the different kinds of analysis that we talked about, and then you plot these different parameters like VDD, R on, all these different things. For all key parameters, you then plot these. In this case, in this example, we are looking at the eye width, the width of the eye in picoseconds on the y-axis, and along the x-axis are different collections of wafers. Typically in a factory, they may be called a lot. One lot of wafer may have 25 wafers, and the 25 wafers may end up having anywhere from 100 die per wafer to 10,000 die per wafer, depending on the size of the die. So you integrate all of that data onto in one location. Now you can do this for one wafer, or you can do this for a whole lot, or you can do different time frames. And so you're plotting this on this, and you're saying, okay, that eye width parameter for this particular lot, which was manufactured 2 days ago, what happens is this is the spread in the eye width, and the mean is here. So here is one where the spread is tighter. Here is one where the eye width is shifted up. Here is one where it's shifted down. So eye widths, you don't want them to be smaller. So these lower numbers are not good. So this cutoff may be to say that anything that's below this number, we need to like discard. But anything that's out here is good. And a measure of how good your process is if you can get this distribution tighter and higher up. And so there are process engineers who will go ahead and tweak their processes to try to shift these plots, to shift them up and to make them tighter. So margin distributions are constructed for different high volume manufacturing scenarios using Monte Carlo simulations based on the computed surface. So here I expanded that. So EW is eye width, and that's basically the same thing that I mentioned. And so here, the blue line is saying that the mean, the middle of this distribution is here, it's higher up here, here. So then engineers will go off and try to figure out what happened that caused this to shift down. Okay, so in summary, signal integrity analysis consists of both component level and system level analyses. Component level analyses solve Maxwell's equations with a discrete numeric approach in 2 dimensions or 3 dimensions. System level analysis, so that's component level. System level analysis allows cascading of the output of one component to the input of the next component through the entire system for through circuit analysis. That gives us the system metrics. Manufacturing and material variations, that's differences from the values that we design or expect, can be captured in DOE analysis, that's design of experiments analysis. And those variations are what tell us, is the manufacturing process good enough to create these chips or not? And if it's not good enough, then there are engineers whose responsibility it is to modify the processes to make it good enough. So PAM, that pulse, the multiple levels of modulation, allows coding of more bits into a single pulse to reduce the component frequency scaling pressure that we had talked about previously. So critical thinking, how do different metrology techniques used to measure signal integrity provide insights into potential issues like signal distortion or noise in semiconductor packaging? And what are the strengths and limitations of those methods? Second question, in what ways can metrology data be used to improve the design and performance of semiconductor packaging, particularly in high-speed applications where signal integrity is critical? Third question, how could advancements in metrology tools and technologies influence the future of signal integrity validation? And what challenges do engineers face in accurately measuring signal integrity in semiconductor systems as they're becoming more and more complex? So as before, these are intended to get you to think more about these topics. We've given you enough information to be able to answer quite a lot of these things. Some of these things you may need to do a little research to go past what we have talked about today. Okay, and so that ends this lecture. With this, yeah, I know this has been a bit of an intense session because we've looked at a lot of math. Okay, so any questions? Okay, I'm going to turn you over to Nick. Nick?
Yep, I'm here.
Okay.
We're going to start our trade journal reading and breakout room discussions. Just a reminder, we'll put you into groups of 4 per room. You'll log into Canvas to access the article links. You'll have 30 minutes to read the article, followed by 20 minutes of discussion, and then 10 minutes to submit your answers in Canvas. You only need to submit the answer to the article that you choose to read. Please make note of which breakout group that you were in, so that if you get dropped from the Zoom meeting, that we can add you back into that group. Awesome. So give me, actually here, real quick, let me put in to the chat the link to the Canvas, as well as the guiding questions for today and those links to the articles as well.
Okay, and while you're all in your rooms, I'll go ahead and look through any questions that you have put into the chat, and I will go ahead and answer them.
Awesome. Starting breakout rooms now.
Perfect. And Nick, do you know how to set up a timer that's visible to the students?
Not one that
do
works in the breakout rooms.
in the break? Oh, I see. Okay. Yeah. Because
Yeah,
I thought, was it you who set up a timer for one of our breaks in a previous session?
I think that was Matt.
Okay. Yes.
I think he
That's
told
fine.
me about that. Yeah. All right, rooms are open, so y'all should be able to join your rooms there.
Okay. Perfect.
Dr. Theodore, are you there to give them your final thoughts on the articles and answer any questions?
I'm sorry, I beg your pardon?
Are you ready to as I've closed the breakout rooms and brought everybody back. Are you ready to close out the articles?
No, actually, I just arrived a little bit late because I was like having a course today for the first day. So I arrived a little bit late. So would you mind like putting me into a chat room?
Oh yeah, we just closed the breakout rooms. I was actually looking for Dr. Theodore. My apologies.
Oh, I see. Yeah.
Oh,
Oh, can
no
you hear me?
worries. Just talk the same. Yeah.
I'm sorry. Nick, can you hear me?
Yes, yeah.
Okay,
The
okay.
breakout rooms are closed, so we're ready to wrap up, I think.
Okay, perfect. Yeah, so typically what I do is I'd have, do you have any announcements that you want to make? And then I'll go ahead and uh, talk about the articles. That way
Yeah,
we
sure.
make, okay, go ahead.
Yeah, sure. Just a couple of announcements. So the Zoom recording from tonight will be posted on Canvas tomorrow morning, Arizona time. The final exam will be open after tonight's session. Please complete that by Sunday. Um, and then there are a couple of final surveys at the end of the course. We would appreciate any feedback you have on the content, on the structure of the course, anything that we can do to improve the quality for future cohorts and for this course going forward. So if you take a few minutes to fill that out, we would greatly appreciate it. Thank you.
Oh, and also the exam, when you say by Sunday, you mean by midnight Sunday, Arizona time, right?
Correct.
Okay, perfect. Yeah, because that turns out to be other times in the different countries that we have
True.
students from. Yeah.
Sure.
Okay. So you're ready for me to go ahead and talk about the papers?
Yep, that's it on my end.
Okay, perfect. Yeah, the papers shouldn't take very long, like no more than 5 minutes at the most. Um, so two of the papers, one of them was what's so different about interposer signal integrity, and the other paper was PCIe over optical transforming high-speed data transmission. So the first one was what is so different about interposer silicon integrity? And the first question was what is the function of the interposer? I just jotted down some notes. The interposer basically acts as a carrier for signal and power interconnects between chiplets. So that's small chips that are put on top of a 2.5D IC assembly. The interposer helps to enable high-speed digital communication between the components, and examples of components include graphics accelerators, network controllers, and high-speed memories. And it also enables analog signals from custom chiplets, that's small chips, such as those that are used in wireless communication, like for instance on cell phones, and sensors. The second question was what typical technology node is used to fabricate the interposers? The interposer, typically the industry uses a technology node that's behind, it's not as advanced as the ones that are used for the logic chips. So, and it's usually a mature process node. An example is 65 nanometer node. The next question, okay, actually that's done with the questions for the first paper. The second paper is PCIe over optical, transforming high-speed data transmission. The question was, how has the advent of artificial intelligence impacted global data creation? And so I just put down some notes. Basically, as AI has really exploded over the last 2 years or so, ChatGPT is the one that most people are familiar with, but there are other models as well. And that has enormously increased the data creation, the rate of data creation around the globe. So the earlier AI models, for instance, with ChatGPT, I think ChatGPT 2.0 was 1.5 billion parameters. It's like the size of the number of neurons in your brain, for instance. the number of neurons in your brain is in the order of about, if I recall correctly, it's about 10 to the 11 or 10 to the 12 neurons, something of that sort. Yeah. So we are still quite far from that. But the current ChatGPT 2.0, if I recall correctly, is 1.5 billion parameters. And then it grew to 175 billion parameters in the current model. That's GPT-4, I think. And future generations, maybe 5, maybe 6, GPT-6. And most of the models from other companies are all comparable now. They are expected to possibly reach as high as 100 trillion parameters. So that is like 1,000 times bigger than the current model. And the parameters, to optimize the parameters, you need to use a lot of data. And also the more parameters you have, the more data these models are able to generate because they are being applied in more and more applications. So this has increased data creation enormously. So the global data collection is expected to be higher than 180 zettabytes. So 1 zettabyte is 1 trillion gigabytes. So we're talking about 180 trillion gigabytes by next year. And this would be a 50% increase over 2023 and a 200% increase over 2020. So global data creation has really exploded as a result of AI. The next question was, as signal transmission distances grow and signal transmission rates increase, what is the potential solution for signal distribution and why? So the answer is basically linear pluggable optics are a potential solution for signal distribution as the transmission distances grow and the rates increase. The LPOs, that's the linear pluggable optics, they have a longer reach. That means the signal can travel greater distance before degrading significantly with minimum latency, so slowing down of the signal, and minimum power consumption compared to the traditional direct attached cables, which are not able to meet the current increasing demands. So what the linear pluggable optics do is they eliminate components like clock data recovery, CDR, and digital signal processing, DSP. And by removing those components, we are reducing the power consumption and the latency. And so this becomes increasingly more useful for high-speed data transfer in the data centers that are getting bigger and bigger and bigger as we generate more data, and also as we apply AI in more and more real-life applications. So that's basically what I had. So if any of you, so I've also answered, I went into the chat and I answered several questions that people had posted. And I see there's one more question about, could you give comments about the mature process using the silicon interposer? And that's basically what I just mentioned, that the interposers are usually a few generations behind the latest leading edge. So I mentioned 65 nanometer node. And so that's significantly behind. The interposer is behind, and that's cheaper. It makes it cheaper for the to create the interposer. And also you don't need as much density of wiring and so on in the interposer compared to in the chip itself. So the chips currently in production are ballpark of about 5 nanometers, maybe in some places 3 nanometers. And the next generation is heading towards 1.4 nanometers. So you can see that that's on the chips, the logic chips and so on. So on the interposers, you can see we are several generations behind, at least maybe 4 generations behind. Okay, any other questions? Okay, if there aren't any other questions, we can end our session 9 minutes early. I hope it's been a pleasure spending the evening here or the morning with you. And we look forward to seeing you next week. And I'm assuming that most of you will be coming next week for the next micro badge. But in any case, good luck to you. Have a good day or a good evening. Okay. You're welcome, Joseph. I just saw your comment. Okay. Have a good night. Have a good day. Bye for now.
Thank you. Bye.
Bye. Bye.
Thank you.
We'll see you.
Thank you, Professor.
Thank you,
Good night,
Professor.
everybody.
Bye, everyone.
Bye. Bye, everybody. Yes.
Thank you so much. Good night.
Thank you so much.
Thank you. Good night.
Thank you.
So much.
You're welcome to those of you who just made comments.